Let's take a look at our radical rows assignment. For this assignment, you're going to be looking across the 8 rows and checking the box of all of the ones that are the same answer, so they reduce to the same number. I'm going to zoom in really close on row number 1 and we'll analyze each step and see if we can figure out the pattern that some of them all fit into. So looking at row 1, the first one is 4 to the root of 2. Square root of 2 is already broken down all the way it can be because this guy's prime. So there's really not much I can do here. So let's keep going and see if this is a similar answer. 2 to the 5th, I have 2 options to solve this problem. I could type 2 to the 5th into my calculator or figure it out 2 times 2 times 2 times 2 5 times. Or I could use the idea that 2 to the 5th is the same as 2 times itself 5 times. So that's what 2 to the 5th really is. And I know that if there is no index up here, I'm taking a square root. So the index is 2. In other words, I need groups of 2 to be able to take 1 out. That means I could take the first one out and the second one out. So therefore, I have 2 times 2, or 4 on the outside, times the square root of 2. Oh boy, we already figured out a pattern here. The first 2 boxes are the same, so I think that's the pattern that we're looking for. We're going to try to see if any of the other boxes in row number 1 reduce to 4 root 2. The next box here, it looks like it can't be reduced any further because the square root of 2 is already reduced all the way. And this is not the same, so I'm not going to check that box. I'm going to leave that alone. Let's take a look at this one. Remember, when you are adding radicals, you need to have the exact same number under here and the exact same index. If you do, you can add the coefficients of the radicals. So, first of all, the hiding coefficients in front of every one of these, there is 1 of each of these numbers. They are all the exact same radicand, or the base, and they are the exact same radical. We're taking the square root of 2. So how many square root of 2's do we have? What's our like terms? We have 4 square root of 2's, so this fits our pattern. I'm going to check that box. And this guy, let's turn this into radical notation. I have a base of 2. I'm going to raise that to the 5th power, and I have an index of 2. If I remember correctly, that is the same as the second box. So this guy and this guy were the same, so I know that this reduces to 4 radical 2, so this must as well. So, in short, we can check that box too. And let's look at the last one, 2 root 8. Let's break down 8 and see if it is the same as all the rest. 8 is the same as 4 times 2. And 4 is the same as 2 times 2. I have then in code here 2 times radical 2 times 2 times 2. I'm taking a square root, so I need a pair to take 1 out. I can take 1 out, and 1, 2 has to remain inside because it doesn't have any pairs. So on the outside I have 2 times this guy, 2, so that means 4 root 2. That is the same as well. So on the first row I checked every single box except for the third one. Let's take a look at row 2. The first thing I'd like to do for row 2 is to distribute or multiply all of the inside exponents by this power of 3. So I want to make sure I have a visible exponent on all of my numbers, including the 2 in the front. And then this 3 is going to multiply. Remember, we multiply our exponents if they live on a parenthesis. The bases will stay the same, so I'm going to leave the 2, the x, and the y the same. And then the exponents change. So 1 times 3 gives me a 3. 2 times 3 gives me a 6. And 3 times 3 gives me a 9. That's all going to be written over 8x to the third. What I'd like to do next is rewrite this as what it really is. 2 to the third is the same as 8, so I now have 8x to the 6th, y to the 9th over 8 x to the third. Let's simplify and see what happens. The 8's divide, and so they turn into 1. They're gone. If I look at my x's, I have more x's on the top, and I have 3 more if I do the subtraction. And the y does not cancel. So I think that this guy reduces to x to the third, y to the ninth. So what we'll do next is we'll move to the next box and see if it reduces to x to the third, y to the ninth. And if it does, we'll check both of those boxes. Oh my gosh, it already is x to the third, y to the ninth. So we have found our pattern. These two problems reduce to the same thing. So now we know what we're looking for the rest of the row. X to the third, y to the ninth. Let's look at the next one. Okay, this may or may not be x to the third, y to the ninth, but that's really what we're looking for in this row. To check if it will work, let's fix this negative and see what happens. If I have a negative exponent, it moves its base to the bottom or the other side of the fraction bar. So that means that the x needs to go on the bottom, and now it has positive 18. Y to the ninth is totally fine, so it stays up top. There's not much more we can do with this problem because these are not the same base, so I can't do anything to combine these exponents. Because I cannot go any further and it is not x to the third, y to the ninth, I will not check this box. Let's check this one. Right away I see that these 8's are going to cancel out, so I'd like to cancel these 8's out. If we divide 8 by 8, we get 1, so my coefficient here is a 1. Next, with the x's, we can take those two numbers and we can subtract, because I'm really dividing the bases, which gives me x to the third and y to the ninth. So that follows the pattern, so that means I'm going to check this box. I'm doing another division problem here. This is like old school division writing. I haven't seen this symbol in a really long time. I think what I'm going to do first is write this out. So I have 8x to the 6th, y to the ninth, divided by 8x to the third. And isn't that the exact same problem as we just did? That's funny. It tried to trick us by using a different division symbol, but really those problems that we just did is the exact same. So I know that this is going to check and be x to the third, y to the ninth as well. All right, let's do some multiplication. If I have like bases, I'm going to add the exponents. So that means x and positive 6 plus negative 3 gives me positive 3. And y to the ninth doesn't have any bases, so he'll stay the same. So that means I get x to the third, y to the ninth for that one as well. So I have checked every single box on that row except for the third one. Let's take a look at row 3. All right. Right away, I see this guy is raised to the 0 power. So I like to circle whatever is raised to the 0 power and remind myself that that is just a 1. So 1 times a to the 4th is just a to the 4th. So this entire bit out here gives me a to the 4th. And then I'm supposed to multiply it by this thing. But I've got a negative exponent, which means take it to the bottom of the fraction. So I'm going to take that and put them on the bottom. And then I'm going to say, okay, well, what does this give me? Remember, when we are dividing like bases, you'll keep the base the same, and then you'll subtract these exponents. Another way to do this and avoid negative exponents is to think about it beforehand and say, where are the most exponents? Where are the most a's? There is a to the 5th down here, so this is a times itself 5 times. There's 5 a's down here. And this is a to the 4th, a times a times a times a. So there are more a's on the bottom of the fraction. So that means my answer is going to go to the bottom of the fraction, and then I can just think about the difference in a positive aspect. So I think that this answer is 1 over a. We'll see if the next box reduces to 1 over a as well. Again, we have something raised to the 0 power, so we can remind ourselves that this is just a 1. 1 times anything is just that thing. And then again, we have the same kind of fraction going on. I've got more a's on the bottom, so the a is going to be there. And when I take the difference, I get 1. So I think those 2 first boxes need to be checked. So now we know we are looking for an answer of 1 over a. 0 is definitely not the answer we're looking for, so I'm not going to check that box. But this guy is 1 over a. That's exactly what I want. This is not 1 over a, and there's nothing I can do with that, so I'm going to leave that blank. The next one, is this 1 over a? Think about it. I've got a negative exponent. A negative exponent says take that base to the bottom of the fraction, and that is 1 over a, so I'm going to check that box as well. It looks like on row number 3, we checked every single box except for the one that was 0 and 1. Let's try row number 4. The very first one on row number 4 is kind of an interesting problem because the 6th root of 8 cannot be broken down any further, and this is a square root of 8. I know that these two cannot be combined as is. However, I have a feeling that we could do a little bit more if we had them in rational exponent form. Remember, to change things from roots to rational exponent form, you keep the same base, so we have 8. And then you take the power, so what is this 8 being raised to? It's just 1/8, so the power of 8. And then you put that over the index. Remember, for this first number here, I'm taking the square root of 8, so that index must be a 2. Now I'm going to leave my times symbol as times, and then I'm going to write the next one as the same kind of format. I have a base of 8, a power or an exponent of 1, and my index on this one is a 6. If you notice now, remember when we are working with fractional exponents, as long as the base is the same, we are allowed to add our exponents together. Now we are allowed to combine these two numbers into 1. We were not allowed to combine them into 1 in rational form because we were forced to have the same index there, but that doesn't matter if it's in fraction exponent form. So it's kind of nice to be able to switch this form on us. I have the same base, so I'm going to leave that base as an 8, and then I'm going to take 1/2 and 1/6, and remember, when I'm multiplying bases, I add the exponents. So I need to do 1/2 plus 1/6. These are not common denominators, and I must have common denominators to add fractions. So I think for the first fraction, I'm going to change this into a 1/6 so that we are allowed to go ahead and add. If I multiply the 2 by 3, I can change it to a 6, so I must multiply the top by 3 as well. So 1 times 3 is going to give me a new numerator of 3. Now I have common denominators, so I can keep that denominator common. Remember, when we are adding fractions, we leave the common denominator even for the answer. And then we're just going to add the numerator. So that's 3 plus 1, or 4/6. I'm really tempted to put that up here as my answer. However, I could reduce this a little bit further. Remember that both of those numbers are divisible by 2. So I think my exponent is really going to be 2/3. So this is 8 to the 2/3 power. Now, I know it's really tempting to be done with this problem. However, I think we might benefit from changing this back into radical form. And I just have a hunch because it originated in radical form. So let's try to put it back into that. When I put this back into radical form, I think about, okay, my base is 8. My power, I'm raising that to a power of 2, and I'm taking the cubed root. And just to see what happens, let's try to see, this would be the same as the cubed root of 64, because 8 squared is 64. If I broke down 64, I know that's 8 times 8, and then 8 breaks down into 4 times 2. Those 2's are prime, but the 4's are not. So I could break those down into 2 times 2, and again. So if I think about it, I really have, the cubed root of 64 is really just asking me, what's the cubed root of, how many do I have going on? 1, 2, 3, 4, 5, 6 2's. So here they are. I'm looking for groups of 3 because I'm taking a cubed root. So for every 3 2's that I have, I can take 1 out. So here's one group. Here's another group. Oh my goodness. I don't really need this radical anymore. And my answer is just 2 times 2. So this entire ugly thing, all of that work, just broke down to one final answer of 4. Wowza. Let's see if any of the other ones reduce to 4. Oh, this one does. I'm going to check the first 2 boxes because those both reduce down to 4. And 8 to the 1/8. Well, that's 8 raised to the first power, and then I got to take the 8th root. Well, 8 only breaks down into 4 times 2, and then 2 times 2. So there is definitely not a group of 8 here. So I don't think I could go any further than this, and that is not 4. So I'm not going to circle that one. Well, let's take a look at this. I claim that this is the first one in disguise. What is this number here? 8 squared. That's just the cubed root of 64. And remember, we already solved this problem. It's 8 times 8. I end up getting a bunch of 2's. We did that in the very first problem. So this does reduce to 4, so I am going to check this box. And the next one, it definitely reduces to 4. Again, I did it in the first problem. If you need to break it down, you can see it again. I've got 8 times 8. This is 4 times 2. And then 2 times 2. I end up with 6 2's. And I need groups of 3's to take 1 out. And so I can take out a 2 and another 2. So that means I don't need my radical anymore. There's nobody left inside. My answer is 2 times 2 or 4. The very last box, these last 2 are the exact same thing in disguise. 64 or 8 squared. I mean, 8 squared right there is the same thing as saying 64 right here. And the last one, 8, that's not the same as 4. So I'm not going to click that box. So for row number 4, I checked every box except for the last one and the one that was 8 raised to the 1/8 power. Every box except for this one and the very last one. Let's take a look at row 5. Starting with the front. What I think I might do here is break down the 16 and see if I can find anything I could take out front. I know 16 is the same as 4 times 4, and that means I've got 2, 2, 2, 2. And then if I want to draw a picture of x to the 5th, that would be x times itself 5 times. So all of these things multiply together to get me 16x to the 5th. Now, I'm taking the cubed root of that, so I'll just draw it down here. That means I need groups of 3 to be able to take 1 out. I've got 3 2's, so I can take 1 2 out. This guy is stuck inside. I've got 3 x's, so I can take 1 x out. And these 2 are stuck inside. So that means I could rewrite this answer as my 2x on the outside times the third root of this loner 2, and then this x times x, or x squared. So I think that's the simplified version of this guy, and we'll see if any of them match. The next one seems really similar, so maybe it might match. If I drew a picture of this, I've got 2 times the third root of x times itself 5 times. And then since it's a third root, I need to take out 3 at a time. So that means I could take out 1x. There's already a 2 out there, and then I'd get left with the third root of x squared. Now be really careful here. These are not the same answers, because this has a 2x squared left inside the radical symbol, and this only has x squared left inside. So this is not the same as this, so far I haven't checked any boxes. On the next round, I could see if I could reduce anything, but looking ahead, I already know that I need groups of 3 primes to be able to take 1 out. 2's already prime, so I can't do anything with that. X squared is already I mean, there's only 2 x's there, so I don't have a group of 3. So this is probably as reduced as it could get. So I have 4x to the third. And the front guy, again, it seems really similar, but this is 2x to the third root, or times the third root. So 2x versus 4x times the third root. I don't think this is the same either, so still haven't checked any boxes. Oh, here's one. This is the exact same as what we got for the first answer. 2x times the third root of 2x squared. So now I can finally check those 2 boxes. This box is the same as the first box. 2x times the third root of x squared. So the first box, and I think that was like the fourth one. Yeah, this one is no, this one is a no, and this one is yes. Okay, let's try the next one. This is not the same, and I could not break this down at all because it's already fully broken down. So move along, and no, okay. This one as well is already broken down all the way. So row 5 seems really weird because you're only checking 2 boxes, but honestly, only 2 boxes are the same. The very first one and then the fourth one. All right, let's take a look at row 6. This is the 12th root of x to the third power. I think the only thing we could do with this is maybe write it as an exponent. So I've got the third over the 12th, and then I guess we could reduce that. That would be the same as x to the 1/4, right? I've got power over index. So I mean, we could look to see if we have any of those, x to the 1/4. Here's x to the 4th, not the same thing. Ooh, I see x to the 4th in disguise. If I reduce that fraction, I've got a 1/4. So I think the first box and the third box are the same thing, x to the 1/4 power here. And then there's another x to the 1/4 power, so I didn't have to do any work on that one. And is this, let's think about if we change this to fraction exponent form. I put the power over the index. This is 1x, so x to the first over the index 4. So this is x to the 1/4 power. I'll check that box. And then finally, I've got this guy, which I could put in fraction index or fraction exponent form. Power over index. And if I reduce, that does become 1/4. So I think the last box could be checked as well. So I checked quite a bit of boxes on that row. The only one I didn't check was x to the 4th, the second box. All right, let's take a look at row number 7. There's not much I can do with this one. I mean, I guess we could write it like this. I have the third power of 3, and then I'm taking a square root. And if we wanted to, we could break this down and take out a pair of x's. So I have an x on the outside times the square root of x. This guy is left inside. This guy comes out in a pair. So that's the only thing I could really do there. Ooh, let's see what happens here. I'm multiplying 2 like bases, so I keep the base the same, and then I get to add the exponents. I have 2/3 and 5/6, so I need to have common denominators. I could change this first fraction into a 6. I multiplied by 2 here, so I have to multiply by 2 on the top as well. So I've got 4/6, and then I can add straight across. Remember, I worked so hard to get a common denominator, I keep it common, so the 6's stay the same. And then on top, I've got 4 plus 5, or 9. If I simplified that, that would be x to the, let's see, 3/2. Hey, that's the same as the beginning. So that one is the same as this one, 3/2 right there. Okay. Awesome. This one I do not think is the same as 3/2. 5 is prime, so I can't reduce that at all. So I'm going to leave that as is. Oh, yeah, remember we reduced the first one to the same thing as this? So we can check that box as well. And this one, let's see. If I wrote this in exponent form, I've got x power over index. I'm taking a square root, so that must be 2. This is x to the 3/2 as well. I'm going to check that box. And finally, I've got this guy, 7 is prime. I don't think I can check that box because that fraction is not reducible. So I checked every box on that row except for the x to the 5/9 and x to the 7/9. All right, last one, row 8. Let's go ahead and multiply for the first box. Remember, when you have a parenthesis, a power on a parenthesis, you multiply those powers together. If I multiply these two numbers together, I could cross reduce those 2's away and I just get x to the 3rd, which of course is the exact same as the second option. So I'll check both of those boxes. Now let's see what happens here. Oh boy, a lot is going on. I think I'm going to add these together first. I've got x. I need common denominators because I'm adding exponents. I already have it, so I'll keep that 5 on the bottom. And then on the top, I've got 3 plus 7, so that's 10. That means inside the parenthesis, if I reduce that, I've got x squared, and then I've got to times that by 3 halves. Again, I get x to the 3rd, so I'm going to check that box. X to the 3rd is there as well. For this one, if I wrote it in exponential form, I've got my base of x, my power of 6 over my index of 2. If I reduce that, 6 divided by 2 is 3, so this is really x to the 3rd. Nice, I can cross that box. Right here, I've got two like bases that are being multiplied, so I'll keep the base the same, and I'll add their exponents. I need to keep common denominators, so I'll keep that common denominator for my answer, and I'll add those together. 9 plus 21 is 30. And then if I reduce, 30 divided by 10 is 3. So this is x to the 3rd, so I'll check that box as well. And then finally, I've got this guy, which I can change to exponential form. Here's my base raised to a power of 30 over an index of 10. And again, 30 divided by 10 is 3, so this is x to the 3rd in disguise. So I checked every single box in that row, every single one reduced to x to the 3rd. Okay, I think I've got it, and I've got my final answers. Some of them are checked, some of them are blank, and that wasn't too bad.